Hello guys, good afternoon to all. Am I audible?
Yes, sir.
Yeah, okay. Okay, so we have ended the third chapter. Uh, Actually मला थर्ड चॅप्टर तसं सकाळी मला तुम्ही डिमांड केली होती की डिस्कस करायचं ओव्हरऑल. बट ज्या पीपीटी आहेत त्या सगळ्या माझ्या कॉलेजच्या पीसीवर आहेत. आणि इथं नोट्स आहेत बट आय थिंक इट इज बेटर टू डिस्कस विथ द पीपीटीज बिकॉज all things we have seen from over the PPT. So on Monday we will discuss this chapter within 15 to 30 minutes. Is it fine? Can I move to the fourth chapter? Okay. So this is the fourth chapter, that is the synchronization. Actually हा चॅप्टर म्हणजे तुमच्या पहिल्या सेक्शन मधला थोडासा सगळ्यात टफ चॅप्टर. कारण की फर्स्ट, सेकंड, थर्ड as compared to these three chapters, this chapter is little bit tough. टफ यासाठी कारण की ह्यामध्ये तुम्ही अल्गोरिथम स्टडी करताय. आता तुम्ही शेड्यूलिंग अल्गोरिथम that we have seen, but we are not studying that algorithm. We are going to study the problem. Okay, actual algorithm तुम्ही त्यामध्ये स्टडी केला नाहीये. But this is the fourth chapter in which we are going to study the synchronization algorithm, and that's why this chapter is little bit tough, little bit tricky. आणि ऍक्च्युली हा चॅप्टर बराच वेळा तुमचे जे कॉम्पिटेटिव्ह एक्झाम आहेत, स्पेशली गेट एक्झाम, ॲटलिस्ट 2 क्वेश्चन प्रत्येक वर्षी ह्या चॅप्टरवर असतात. ॲटलिस्ट 2 क्वेश्चन. माझं पॅटलॉग आतापर्यंत हे आहे की 5 वेळा, 5च्या 5 वेळा माझ्या हातले सगळे क्वेश्चन करेक्ट आले नाहीयेत. एखादा क्वेश्चन करेक्ट येतो, सेकंड क्वेश्चन 90-95 पर्यंत 99% पण करेक्ट सॉल्व्ह होईल, पण शेवटच्या 1% साठी क्वेश्चन चुकतोय. त्यामुळं हा चॅप्टर स्टडी थोडासा व्यवस्थित स्टडी करावा लागेल तुम्हाला. अँड more important, what are the algorithms that we are going to study in this chapter? We have to understand all this conceptually. ओके, कन्सेप्ट थोडेसे डिफिकल्ट जरी असले तरी आपण जास्त पण इनडेप्थ जात नाहीये. ओके, कारण जास्त इनडेप्थ गेलं तर सगळ्यांना परत बाउन्सर पडतात हे बघितलं मी. त्यामुळे 2-3 वर्षाचा माझा एक्सपिरियन्स आहे की जरा ते थोडीशी डेप्थ वाढवली की आपोआप सगळ्यांना बाउन्सर पडतं. त्यापेक्षा बेटर ऑप्शन आहे की जेवढं अंडरस्टँड होईल तेवढंच लर्न करूया. ठीक आहे. सो दिस इज चॅप्टर इम्पॉर्टन्स. chapter okay, we have in second chapter we have studied the inter-process communication. Okay, since we are dealing with the many processes in the system, whenever you are going to design an application, then definitely in that application we are performing the modelization. And modelization is what we are uh, uh, developing a different processes. We are generating different processes for the carry out to specific tasks, so that by performing all these tasks, or the application which want to perform uh, uh, to carry out some work using all this process, it can carry out. So in the application, by performing the modulation, we are creating different processes, and since the different processes are present, definitely we need a synchronization. And we have seen that to perform this, we need a inter-process communication. During this inter-process communication, we need a synchronization between all the processes. Because without the synchronization, what can happen? We can understand using this example. Okay, so first understand why this current scenario is important. रिझन इज सिम्पल. जेव्हा आपण कोणतंही ॲप्लिकेशन डेव्हलप करतो, ॲप्लिकेशन म्हणजे एक कम्प्लीट वन प्रोसेस होत नाही. ओके, आपण ते ॲप्लिकेशन डिफरंट मॉड्यूलमध्ये डिवाइड करतो, अँड दॅट वन मॉड्यूल इज नथिंग बट मे बी युअर वन प्रोसेस. वन मॉड्यूल और वन प्रोसेस, दीज आर डेडिकेटेड टू अ पर्टिक्युलर टास्क, आणि तेवढं टास्क ते कम्प्लीट करतं. अँड बाय इंटरकनेक्टिंग ऑल दिस मॉड्यूल्स, your application is developing. Now, it is important that in the inter-process communication, all these modules or all these process should be communicated. Without communication, the task cannot be completed. फॉर एक्झाम्पल सपोज तुमच्या मॉड्यूलमध्ये किंवा तुमच्या ॲप्लिकेशनमध्ये एक मॉड्यूल आहे ॲडिशनचं आणि दुसरं मॉड्यूल आहे सबस्ट्रॅक्शन. तर ह्या केसमध्ये ज्यावेळेस तुम्हाला एखादा टास्क कंप्लीट करायचा असेल आणि त्या टास्कमध्ये तुम्हाला ॲडिशन आणि सबस्ट्रॅक्शन दोन्ही केसमध्ये दोन्ही तुम्हाला टास्क परफॉर्म करायचे, देन यू नीड सिंक्रोनायझेशन बिटवीन these two modules, these two process. You need definitely ह्या दोन्ही प्रोसेस एकमेकांशी कम्युनिकेटेड आहेत. We have seen to different technologies like message passing communication system as well as shared memory communication system. Using these technologies, two processes can be communicated. But when they are communicating with each other, the process should be synchronized. Now, what I mean by synchronization? What is the need of synchronization? We can see through this example. Okay, so suppose you have two modules or you have two processes in which one process is performing the addition operation, that is counter plus plus, and second process is performing the subtraction operation, that is the counter minus minus, and definitely the counter, it is a shared variable. Okay, this counter is a shared variable. Now, when this shared variable is sharing in between these two processes, and suppose this our system is in this operation is performed on a single core, then we know that at a time only one process can be executed. So suppose we are executing this process in the manner of as shown in figure, that is the process 1 or program 1 that I started to execute first. After that, after some time duration, the program 1, it gets switched, context switch occur, and program 2 started the execution. Again, after the time slice expired, program 1 again start to execution from its previous start, and again get context switch after the time slice expired, and so on. Okay, so these two processes can be executed like this. Now, when we are performing this task, that is performing the addition operation as well as performing the subtraction operation on shared variable, suppose the value of counter is 5. Initially, we have initialized the value of counter equal to 5. Then, in the normal scenario, if you perform the addition operation and subtraction operation once, then it is expected that the value should be 5. For example, suppose counter 5 that is initialized and program 1 is performed. Then after executing program 1, the counter is incremented. So from the value 5, it will get incremented and value will be a 6. Now after program 1, suppose program 2 executed, then the value 6, it will be decremented by 1. So output, it will be a 5. So it is expected that after performing these two operations once, the value of counter, it should be a 5. Okay, that is our expected output. But it may be possible that the value, it may be a 4 or it might be a 6 if it is not executed in a synchronized manner. Okay, so let's see how this value, it may be a come. आवाज जर मध्ये ब्रेक झाला तर त्या केसमध्ये सांगून द्या. ओके, कारण की ह्या चॅप्टरचा स्टार्टिंग सगळ्यांना समजणं महत्त्वाचं आहे. स्टार्टिंग जर नाही समजलं, परत पूर्ण चॅप्टर तुम्हाला समजणार नाही. दॅट्स वाय दिस लेक्चर इज इम्पॉर्टंट. इफ माय साऊंड इज नॉट क्लिअर, okay, suppose now suppose the same example by using some low language instruction, or we can say by using the assembly instruction. Okay, this counter program plus plus or minus minus, this is the program in a high level language, and definitely by performing different operations, by converting this high level language into the low level language, we will get the output in assembly level language. So suppose this counter plus plus we are converting into the assembly language. Similarly, counter minus minus, same instruction, same statement we are converting to the assembly language statement. So this will be the assembly language statement for the counter plus plus as counter minus minus. So counter plus plus, the assembly language statement, it will be a R1 where we are storing the counter, then performing the operation R1 plus 1 and stored in the R1, that is register R1, and from that R1 it will store into the memory location counter. Similarly, for the decrement, we will have the assembly language instruction as first, from the memory location counter we need to shift the value into the register R2, then perform subtraction operation R2 minus 1 and store the value in same register, that is in R2, and after that from the R2 register store that value at memory location counter. So this is the converge instruction of the high level language statement. Okay, so if we perform the operation, okay, if you perform this low language statement, if you execute this statement, if you execute the instruction, then as our normal scenario, first program 1 will be executed order by order, that is from the counter 5, from the counter where the value is 5, that will be shifted, or that will be transferred to the register R1. Then in register R1 5 is there, so 5 plus 1, second instruction will be executed where 5 will be and stored again in the same register. After that, from the register R1, the value will be stored at the memory location counter. So value in the counter, it is a 6. Then context switch occur. After that, the value of counter, which is 6 in the memory location, that will be transferred to the register R2. Then decrement operation performed, that is R2 minus 1. So 6 minus 1, it will be 5. Again that value will be stored in the register R2, and in the next step this R2 value will be shifted from register R2 to the memory location R1, that is 5. So in this case the value or the output is 5, that is our expected output. Now consider the second scenario. In the second scenario, suppose the context switch is occurred after the first instruction. Okay, total we have the 6 instruction, and suppose that after the performing the after the execution of first instruction, that is copying the value from memory from the memory location counter into the R1, the context switch occur. Then in the R1 the value is 5. Counter has the initial value 5, and that we have copied into the register R1, and context switch occur. Now the second state, after the context switch occur, the next statement that we is going to execute, it is the R2. In the R2 the counter value is going to transfer. So again here the value of counter is 5. Okay, value of counter is still 5. So that 5 value, it is copied into the R2. Then decrement operation performed 5 minus 1, it becomes 4, and that 4 value which is stored in the R2, it will be copied into the memory location counter. So now the value of counter at memory location, it is 4, but in R1 the value is 5 because we have already copied that value. So in the R1 the value is 5. That's why when the context switch occur after the fourth instruction, that is next instruction is the incrementing the value that is stored in the R1, and the value in R1 is the 5. So after incrementing, the value will become 6, and that 6 value now it will be overwrite at the memory location which was holding the value 4. So the last value at the memory location counter is 6. Are you getting? Okay, so last value that you will get in the memory location counter, it will be a 6. So this is happen because the context switch occur at wrong time. Okay, there may be possible that the context switch that may be happen at the wrong position, wrong location. Then in that case, the output may not the output, it may not the output that we get, it not be a expected output. Okay, so this is scenario when the counter is getting the value 6. If you consider the second scenario, okay, so consider the second scenario in which the program 2 is executing first, try to executing first before the program 1. Okay, in the earlier case where the counter is 6, program 1 is executing. And suppose in this second case, the program the program 2, it is executing first. Now in this case, if you consider the same scenario in the normal case, okay, normal case मध्ये समजा आधी तुम्ही R2 प्रोग्राम 2 एक्झिक्यूट केला असता, काउंटर 5 व्हॅल्यू होती, डिक्रीमेंट केलं 4 झाली, आणि जरी प्रोग्राम परत 1 एक्झिक्यूट केला, अगेन इट बिकम 5. तर त्या केसमध्ये प्रोग्रामची ऑर्डर पहिल्या केसमध्ये नॉर्मल केसमध्ये पण आपल्याला अफेक्ट करत नाही एक्सपेक्टेड आउटपुटला. बट हियर सपोज in the second case, okay, here in this case, suppose program 2 I started execute, and in the first instruction I store the value of counter in R2. Then here in this case, my value in counter is the 5 value I am storing at R2, register R2. And after that, suppose the context switch occur. After that, context switch occur. Okay, here by mistake R2 is there. Here it is considered as the R1. Okay, so so after this, the context switch occur and program 1 start to execute. And in the program 1, the operation performing is again copying the value from counter into the R1. Okay, here consider as the R1. So again in the R1, the value will be 5. Then perform the increment operation, value becomes 6, and store that value 6 at memory location counter. Then context switch occur. After that, the instruction is executing at memory location at register R2, and in R2 the value is 5. Perform the decrement operation, 5 minus 1, it becomes 4, and at the last, the counter and R2 value that will be stored in the counter, that is 4. So in this case, if you start the execution of program 2 first, then the value that might get, it will be a 4. So if there is not proper synchronization, then it may be happen that the output that you are getting, it may be a different or it may be a erroneous. So that's why when the shared variable is sharing between two processes, then it must we take care that or we need to apply some technique so that we can get a expected output or correct output. So that's why the synchronization is important. Now we can understand this case with respect to this risk conditions and synchronization. Okay, so what is meant by risk condition? So a risk condition, it is situation where several processes access and manipulate same data, or we can say the shared data. Okay, in rest condition, it is situation in which several processes they are trying to access the shared data. That we have seen in the example, that is counter, which is shared variable, and if suppose that counter is accessed by program 1 and program 2 at the same time, then we can say that that is a risk condition. All the processes trying to access the same data or shared data. We also call it as the critical section. So critical section, it is the section in our program in which the data that is going to be shared is present. That section is called as the critical section, and rest part is called as the remainder section. Okay, what is critical section? Critical section is a section in which the shared data is present in simple case, or you can simple language. And rest part of the program is called as the remainder section. The outcome depends on the order in which the access takes place. Okay, in the risk condition, the outcome, it depends on the order in which the access to that data is taking place. We can prevent this risk condition by synchronization. Now, what is in the in case of synchronization? In synchronization, it ensures that only one process at a time can manipulate the critical data or shared data. What is in synchronization? In the synchronization, it is ensuring that only one process at a time can access the critical data or can manipulate the critical data or shared data. No other than or no more than one process should execute in critical section at a time. That is the synchronization. Only one process at a time can access the data. That is nothing but your synchronization. Okay. Now this race condition is not occur only a single core. It also can occur in case of multi-core, or we can say it is more possibility that the race condition it can occur in the multi-core. For example, in this case, you can see in the diagram that if there are two cores or there are two processors on which program 1 is executing on one process and program 2 are executing on another processor, then it may be happen that the both program try to access the counter shared variable at the same time. At the same time, they can. It may happen that at the same time, both process or both programs is accessing the counter variable, and and this may possible in case of multi-core as well as in single core. So this condition is called as the race condition. Okay, now understand what is the critical section. So already I explained that in the critical section, only the data that is going to be shared is present. What is critical section? Critical section is a section of a program. It is a section of a program in which the shared data is present, or data that is going to be accessed by, or that is going to be shared by all processes is present, or more than one process, not all process, more than one processes. that part or that section is called as the critical section, and rest part of the program other than critical section is called as the remainder section. Now, when we try to solve this program of the critical section, then whatever the solution that you are going to provide, that solution should satisfy the following requirements. Requirement first, mutual exclusion. What this condition says, in the mutual exclusion, no more than one process in a critical section at a given time. What the mutual exclusion says, in the critical section, only one process can be present. Nothing but the critical section can be accessed by one process at a time only. At a time, only one process can access this critical section. That is called as the mutual exclusion. No more than one process in critical section at a given time. Only one process should be there. The second condition, that is the progress. Progress ensures that when no process in the critical section, and if any other process that requests to enter into critical section, then that request must be permitted without any delay. What is the progress condition? In the progress condition, it says that, or it ensures that, if there is no any process is executing in the critical section, and if suppose other processes is requesting to execute in that critical section, then that request must be satisfied without any delay. That is called as the progress. And the third requirement, that is the no starvation, no starvation on bounded wait. It ensures that there is an upper bound on number of times a process enters the critical section while others are waiting. What is this condition says? This condition says that when there are other process is waiting for the critical section, then in such scenario, the process which is executing in a critical section, it has some limit, it has some upper bound at which the process can be entered into the critical section. Or we can say this condition ensures that the process which is waiting for a critical section, it should not be a starved. It should not be going to the starvation. That should be get executed. So that execution is ensured by this third condition, that is providing the upper bound on number of times executing in the critical section. But when other processes are waiting, then only this upper bound will be set. Are you understood this? Okay, is my sound clear now? Interrupt होते कुठं? Break होत नाही ना sound? Is my sound clear? Okay. Okay, now to provide the solution for the critical section, okay, we have the different solutions. Okay, different solutions are provided time to time for the synchronization purpose. So the one of the solution is applying the lock, that is locking and unlocking the system. So the one more variable that we are going to use in this case is the lock variable. Okay, the different process that is going to that is going to use this locking variable for the synchronization purpose. What is the scenario? So scenario is that whenever any process trying to access any shared data, then it must perform lock on that shared data. What is the scenario? Scenario is that whenever any process is trying to access any shared data, then if you got the access to that data, then first it should lock that data so that all the other process, those who want to access that data, they should not get access, because that lock is prevent access of that. So the process who want to use that shared data, first they want to execute the locking process, then perform the operation that you want to perform, and after performing the operation, the process should unlock the shared data. Okay, so lock L, it acquire lock exclusively so that only one process with the lock can access the critical section. And when the execution is finished, when the accessing of that shared data is finished, then release the lock by executing by executing the unlocking processor, release this exclusive access to the lock L and permitting other processes to access the critical section. Okay, so once the process unlock the shared data, then other process can use the shared data. And definitely when other processes are using the data, they also need to first log that shared data. So likewise, the synchronization can be performed. Okay, once the process log the data, then other process cannot use that data, or it cannot access that data. Then the program will execute its task related to that data, and after the completion of that task, it should release the data so that other process can access it. So by using this locking and unlocking scenario, we can ensure the synchronization between these two processes. We can expect that the output is a legal. The output will not be incorrect. We can get the correct output. Okay, so this is the one of the solution that is provided, locking and unlocking. Okay, but definitely this is not the 100% correct solution. There are many cases that this process or this solution it gets failed. Okay, so that we'll discuss in the next chapter. Sorry, next lecture. We stop here. Give me the attendance. Roll number 1 from A division. Roll number 2. 3.